तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
We said today we will talk about programmable logic devices, programmable logic arrays. We talked about programmable ROMs, programmable read-only memories yesterday, last lecture. The use of programmable ROMs in design of combinational logic. The next PLD, the programmable logic device, which we will consider, is called a programmable logic array. Written as PLA for short, programmable logic array. See, in the ROM based design or PROM based design, as the number of inputs increases, the number of min terms increases, not linearly, is the power of 2, right? So it's sort of an exponential increase. The size of the ROM depends on the number of inputs and the number of outputs, but as the number of inputs increases, the size increases exponentially. Of course, if the number of outputs increase, as the number of outputs increases, the size increases only linearly, because it is the width of the word that you write in each location. The width of the word that you write in each location is the output. The number of words in the ROM is the number of min terms for that particular number of inputs, which will increase to the integer power of 2. So what happens is, when the system is a little complex, let us not say complex, big, large number of inputs and outputs, the size of the ROM becomes very large. Earlier times, the size was an important criterion because it was expensive to make bigger and bigger ROMs. Because even now, if you can save on the size of the ROM, you can save. Why should you unnecessarily spend silicon if you can do it in a smaller chip? The size also takes a lot of memory space, a lot of space in the IC, which you don't want to do, because you would rather like to use that space for some other function. And anyway, switching activity increases because of the power consumption, everything. So there is a case for making the ROM as small as possible from point of view of everything, cost and power saving, etc. But then if the number of inputs are given, there is no way we can reduce it. We have to generate all the min terms possible and then find out which of the min terms need to be combined for each of those outputs. But in practice, we find that any output, especially in the system is large number of inputs and outputs, we find that the given output is only dependent on a few minterms. Very rarely is it a combination of a large number of minterms. So that means even though we are generating all the minterms for a given number of inputs, each of the outputs will use only a few of them. That means many minterms go unutilized or unused. That means we are generating more terms than required in the design. So thereby came the concept of programmable logic arrays. In the programmable logic arrays, the AND array, so you remember the programmable read-only memory, PROM based solution, we had an AND array which produces all minterms and an OR array which was used to program the exact minterms that are required for a particular output. Now if you can make the AND array also programmable, instead of having a fixed AND array to generate all the possible minterms, if I make a fixed programmable AND array and the programmable OR array, then I can reduce the number of minterms to be generated depending on the given function. For that given function, for that given set of outputs, look at the outputs to be generated and only those minterms will generate. Do not even generate the other outputs, other minterms, meaning I can reduce the hardware. This is the concept of programmable logic array. So given as a block diagram, supposing these are the number of minterms, I mean inputs, 3, in the previous case, in the OR based solution, the ROM based solution, would have generated M0 to M7, which would be combined in a OR array to make different functions. Here what I will do is, I will generate a fewer, let us say 4. That depends on how many and what are those terms, will depend on the function to be implemented, the outputs. And those will be combined in the OR array. So this is programmable, this is also programmable. Earlier, this was fixed and this was programmable. In this case, this is also programmable, this is programmable and this is also programmable. And again we will have the now question is, I need to reduce the given function or given set of functions in order to decide which are the terms which I need to generate. They need not be minterms. Now I will have to do a simplification, which was not done in the case of ROM array. In the ROM implementation, I said you don't have to do any simplification. All you need is a truth table. If you get the truth table for each combination whether the output is present or not, if you know, then you generate all those minterms anyway, and then tie those minterms together, which are going to make an output for a particular output. Now in this case, I will do an extra step of simplification using corner map and generate only the smallest number of terms which are required to make all the functions possible, to realize all the given output functions. So instead of calling them M0, M1, M2, M3, they are not minterms anymore, they are product terms. So I will have to call them P0, P1, P2, P3, which are again functions of the inputs. So if we call this ABC, as we always do, P0, P1, P2, P3 will be functions of ABC. Now the step is to get the function, get the specification, get its truth table. The ROM implementation will directly go from truth table to the hardware. In the PLA implementation, programmable logic array implementation, you go through a step of minimization and reduce the functions to a set of minterms and set of product terms which are necessary to implement those functions given F1, F2, F3, F4. For example, in this case it's F1, F2, F3. So F1, F2, F3, also I will just put generally F. Okay, one more advantage is, if some of those terms for F1 and F2 product terms are common, I need not generate it 2 times. I can only generate it once. You can also generate, in fact I can make a more efficient design by having as many common terms as possible. Do you understand? So when simplifying F1, F2, F3 corner maps, I will not have the reduction gate in mind. Reduction in the product terms is an important issue. At the same time I will keep in mind, is it possible to have same min terms, same product terms appear in more than one output function, which means I can share the output for the product terms in different outputs. So also take into account shared product terms. So let us do a simple example of 3 variables. I have I have 3 variables A, B, C. So I will have 3 functions F1, F2, F3 to be implemented with 3 variables A, B, C. Let us say my truth tables are given as follows. F1 ABC is sigma min term zero to, only 2 min terms are required. F2 ABC would be sigma min terms 0, 3, 4. Three, 4, 5, 7. Now, if I draw the corner map for each one of them, corner map for F1, zero, 1, 2, 3. So this is what? A bar? A bar? Pardon? A bar, C bar? Yes. Why are you hesitating? F2 would be zero, 1, 2, 3, 4. Is that what I said? 0, 3, 4. Okay. This will be what? B bar, C bar, or A bar, B, C. And I have a third function zero, 1, 2, 3, 4, 5. This is the F3, isn't it? What will this be? This would be A, B bar plus BC. So how many different min terms are product terms are there in implement all of these functions? 1, 2, 3, 4, 5. I need 5 product terms. Instead of generating 8 min terms and combining them with 0, 2 here, 0, 3, 4 here, 3, 4, 5, 7 here. I can generate 5 product terms, which are even simpler than the 5, 7, 8 min terms, because min term will require a bar, b bar, c bar, 3 variables always. Here this requires only 2, this requires only 2, this requires only 2, only here it requires 3. So I not only I am going to use less number of AND gates, so this programmable AND array will have less number of fewer AND gates, and size of this AND gates is smaller compared to the previous implementation using ROM. So I will have here now, give my ABC as inputs to the AND array, and get out of this the product terms P0, P1, P2, P3, P4, where this I will call P0, this I will call P1, call P2, and then my OR array would tie. There are 3 outputs. This is my F1 to F3. F1 will be P0. F2 would be P1, P2. F3 would be P3, P4. Now I have the implementation of the function. The size is now smaller for the same function, 4 functions. If I had used a ROM, I would have used 2 or 8 min terms and 4 outputs. So size would have been 2 power 3 times what? 2 power 3 times size of ROM. Yes. No, but you don't say 24 because you don't know how many rows, how many columns, how many. You don't multiply the whole thing, and so 2 power 3 times 3. That you have to say like that. Only then you can say take a ROM with 3 inputs and 3 outputs, 3 address lines and 3 output terms. So size would have been 2 power 3. Here it is 2 power 3. It's not 2 power 3. It is 5. 5 product terms times 3. So you have number of bits, the size in bits is smaller here, and each of the decoder, the decoder which does the min term combination from the AND array is also smaller now in case of because it requires to do only 5 terms rather than 8 terms with varying sizes and gates. Now if I want to add one more function to this F4, suppose I want to now have a 4 output. So I need to simplify this map also. This should be 0, 1, 2, 3, 4, 5, 6, 7. Now, what is this? So what is this? F4 is B bar, C bar or BC. Is it not? B bar, C bar or BC. Is that right? And B bar, C bar is already there. P1, BC is already there, P4. So it is same as P3 plus P4. So with these min terms which are already generated, with these product terms are already generated, 4 product terms already generated. Okay, thank you. P1, P4. With the product terms are already generated, P1 and P4, I am now able to get one more output. That is why I drew this little larger box, so I can insert this. F4, which would be P1, P4. This is what I mean by common product terms. If you have common product terms between two functions, you don't have to generate it. This term P4 and P1 and P4 need not be generated again because they are already there. All you have to do is to use them. So we have the advantage, the size is smaller, the AND array size is smaller, and number of gates, not only the number of gates but the size of those gates, individual gates, number of inputs to each of these gates. This will be significant if the number of inputs are large, which is the case in the case of practical systems. Just because you take a simple example in the class, you can be completed in a short time, draw any diagram on the board, does not mean all systems are like this. There is only conceptual diagrams. In a real design, you will have many more variables, input variables, and so the number of product terms, if you want to do a ROM based design, it increases exponentially, explodes. So there is real advantage because however big the system may be, number of inputs, number of outputs, a given output will be dependent always on a few inputs, not more than a few inputs at a given time. It will be localized inputs for that particular output, and then the another output will move and then one more setup. So why generate everything every time and only use a few each time? That was the concept of programmable array logic. The size of this would be, here you have to say size is 4 product terms. I should have the capacity to have 3 inputs. So how do you express the capacity here? Here the ROM, you express the capacity as 2 power n times m, where n is the number of inputs and m is the number of outputs. So if you want to do a ROM based design, don't do a multiplication of 2 power n times m, then you don't know. You cannot go to the shop and ask for a 2 power 3 times 4 is 8 times 4, 32. You can't go and say give me a 32-bit ROM. You can say give me an 8 by 3 ROM or 3 input, 3 output ROM. Like that, in this case I should give the number of inputs, number of product terms it should make, and the number of outputs. So I should give here 3 inputs, 5 product terms. I should be able to generate 5 product terms using these 3 inputs, and then I need 4 outputs. This will be how the size will be determined.
What would happen if we had to add, instead of this function that you've chosen for F4, if we had a function where a combination which is not available in these...
Yeah, you have to. I am just giving you an example of how your function can be shared. That is why I have these 3 which are different.
No, when the...
I cannot add anything for any time, even now. The adding is not after you designed. This was a requirement, and now this is another requirement. I am showing you the same IC can also do the job provided we have one more output.
At the time of manufacturing, it is decided what...
Manufacturer will give you general sizes. Manufacturer will give you 3 input, 5 product terms, 4 output scheme. You will have a different, of course you cannot have all possible inputs and all possible product terms, all possible outputs. Infinite number of combinations will not give you. It will give you a reasonable choice. Give you, I have product, 4 product, in 4 term, 4 input terms PIL are available, programmable logic arrays are available, PLAs are available, 6 are available, 8 are available, 12 are available, 16 are available, you choose. Similarly, they will say, for this 6 I have a variety of product terms, 4, 8, 6, 10. And for each one of them they will also give me 4 output. So there will be a whole variety of commercial products available. You have to choose the best one. It is not that you go and get a shop for a particular device that you have in mind. I will put it the other way. I should have a programmable array logic which will at least have 3 inputs, at least can generate 5 product terms, and at least have 4 outputs. The smallest within that restriction constraints, I will buy. You understand? Supposing there is no 3 input programmable array logic is available, programmable logic array PLA is available, I will use a 4 input. Supposing 4 input is available, I will take that. I will take that and use 3 of those inputs. Otherwise, how do I do this job? Even the RAM, the same thing. I can't say 7 input RAM. 2 power 7 size, it may not be available. Standard inputs 4, 8. Size of the RAM is not available at your will. There are fixed sizes. You have to choose them. If you cannot fit it in this smaller RAM, go for a bigger RAM. That means it's not like a notebook you want to buy from a store. You want 100 pages or 200 pages? Can you buy a 147 pages notebook? Because the teacher is going to teach 147 pages. It's not possible. There's always when you take a package, you want to go buy Coca-Cola also. You have to take a 6-pack or 4-pack. You can't have a 5-pack. It's always the case.
Then how do we know what is the product that each product term represents?
You are supposed to do the design before you go to the shop.
No,
The problem is given to you. I have a problem with 3 inputs, 4 outputs with these following 2 tables. I sit down, take a piece of paper and pencil, if you have one, reduce these min terms, product terms, and then come up with a list of product terms for each output. Then I come with this table, PLA table. Input ABC, product terms will be generated, and product terms will be combined for F1, F2, F2. They call the PLA table, programmable logic array table. You have to generate a PLA table which will give you inputs, the product terms. Suppose I can say PLA table will look like this in this case. I will write the PLA table for this function. PLA table would be P0, F1, F2, F3, F4, P0, P1, P2, P3, P4, right? We have only this much. So F1 will have only P0. F2 would be P1 and P2, correct? F3 is going to be, tell me, F3 is P3, P4. F4 would be P1 and P4. Now I know. So I need to, inputs are given. For a given system, inputs are given. PLA table. I will also note P0, P1, P2, P3, P4 are functions of 3 variables. Even though you may not use all the 3 variables, they are functions of 3 variables. ABC. This is the table I have gotten after designing it. Then this is the information from where I start. I know that I need 3 inputs. I know that I need 5 product terms, and I know that I need 4 outputs. So I'll go to a electronic component store, ask for a PLA with 3 inputs, 5 product terms, and 4 outputs. That fellow will say, no, I don't have one. I have 4 inputs, 6 product terms, and 4 outputs. Do you want to take it? Then I have to take it if I want to really do the design. But you really don't do that. Actually, you do there's a catalog available. It used to be big thick book when we were students. Now it's all in web. You go to the web and say this is my requirement. They will spit out the part number of different manufacturers, and then you choose that person who is, and then that particular device which is, you say this is the minimum requirement and give all the possible combinations. Then they will give you, there is one like this, 4 input, 6 product terms and 4 outputs. Would you like to take it? Then you say yes, and then you probably today you can order it online and give your credit card number, and only thing they have not invented is to deliver the IC through the computer. All other things are there. Somebody has to deliver it with a courier. That is probably will come out sometime. You open your computer and you can pick up the part that you want. Probably that is left for you people to research on when you come to. Do you understand now the problem clear and still confused? You are not convinced. Anybody else has questions on this?
So the outputs that means are programmable in a sense.
Everything is programmable. Product terms are programmable and outputs are programmable. What is programmable is which of the product terms you combine is programmable. I can have up to 5 terms in each of my outputs.
And that can be any combination.
Any combination. I can have F1 is equal to P0 plus P1 plus P2 plus P3 P4. Again F2 is equal to P0 plus P1. Of course you won't do it. You don't want all the 4 outputs to be same. In principle I can have each of those outputs have 5 product terms. But it so requires my combination, my specifications requires only this type of things. Up to 5 inputs I can connect. Each of the product term can go as an input to the OR gate for each of the functions. There is the programmability similar to the ROM programmability. ROM programmability understood the last lecture. Same. There is no change. There is an additional programmability here. Instead of getting M0, M1, M2, M3, M4, M5, M6, M7 and if M16 it is 4 input, I am now going to have P0, P1, P2, P3 stop because I need only 4 product terms or P0, P1, P2, P3, P4, P5 stop. So how many product terms you need in order to, with taking into account common terms as possible. So I will do a in fact we talked about it in the design of a combination logic also. When multiple output combination logic you design for same set of inputs, you will try to share the terms to the extent possible. Sharing the terms will give you reduced hardware, is it not? Supposing I have 4 inputs and 7 outputs, in the case of binary to 7 segment decoder, there if I can share some of those outputs for each of those terms for each of those outputs, that extent I don't have to reproduce that gate again. Same concept here. Even if we leave the sharing part out, I don't have to generate 7 product terms. I only generate as many min terms, as many product terms as required for my implementation. So to that extent there is a saving in the number of AND gates and the number of inputs to each of those AND gates. Earlier in the ROM case, I needed to have 8 AND gates and each of those AND gates had to have 3 inputs. So when you take a 2 input or 3 input case, it is very hard for me to justify. Looks trivial and marginal. But as I said, all practical systems, many practical systems will have huge number of inputs. And you want 16 input combination logic. What will be the size of the ROM? Number of words is 2 power 16, which is 64K. Now if I can produce the whole thing in 50 product terms, what a difference from 2 power K to from 64K to 50. The dramatic change in the hardware requirement. Okay, and that is why it's called programmable. Programmable not in any other sense. I choose my product terms instead of blindly taking all the min terms. And here again I choose the product terms to go into each function. That way it is programmable and this is programmable. So programmable and unprogrammable. Now there is one more product of the same type, programmable logic device, which is called, for some reason they can't think sometime. They didn't know how to name it. First they call it programmable read-only memory because all the possible inputs can be given and then all the possible. Then they said logic array is programmable. Then instead of changing this programmable array logic array, they change it to programmable array logic. They interchange the 2 terms, 2 words. The last. The third variety is called programmable array logic. PAL. The other one is PLA, this is PAL. What is the need for a third variety? Here I need, in the ROM I have one programming feature. Once I know the size of the design, number of inputs and number of outputs, I go ask for a ROM of 2 2 power 7 times 8 or 2 power n times m, get it, and I know all the minterms are available, and all I have to do programming is combine those minterms for each of those outputs, the m min outputs. It was easy to do it, even though your hardware inefficient. It is a hardware inefficient design. Efficiency of the hardware is not good. So they thought we'll save on the hardware, and they said I will do two-step programming. First I will choose what are the AND product terms I need, and then choose it, and then I will combine them. So two-step programming. Again, when the size is very large, number of inputs and number of outputs are large, number of product terms are large, like 50 I sold, 16 inputs, 50 outputs. First of all, you have to reduce them properly. And then you have to find, if possible, as many common terms as possible. Of course, everything is programmed nowadays in computer. In that sense, the other programming, computer program. Instead of manual labor, anything which is repetitive nature, checking for example, computer does better than us because it doesn't get tired of it. We get tired and make mistakes. The number of things you do is very large. But anything which innovates, anything which when you need to apply your mind, you are better than computer, hopefully, right? So that one were not also, people are saying very inefficient. So I need to do this and balance that, and then I may always not end up with a efficient design. So I ended up with an inefficient design. Somehow the programmable array logic is all market driven. One should remember, electronics or any industry for that matter, even pharmaceutical industry, it is market driven. If it is a low cost drug for a cure or something, it gets popular, even though everybody else wants it, but at least it's affordable and people will buy it. So market driven. So when they thought when ROM solution was costly, quote unquote costly those days, these days it's not costly, but it is more area. Why do you want to spend more area and power? They thought this solution will catch on, but it was failure. From the market point of view, it was a failure. A lot of people had difficulty in using this. They had to generate software to do this, all this. Whatever I am saying, it will be done. Reduce it, find out the min terms, product terms, common product, all those I am saying. But in a large system, all of those things will be done computerized automatically. So they found it difficult to write efficient software for that. So there are not many takers. So they thought that is like giving too much freedom. Earlier we had restriction, programmability was restricted. The only difficulty was we had too many things and we didn't want more. We didn't want so many min terms because many of them were not used. So they gave another degree of freedom. 2 degrees of freedom was given. First degree of freedom for the AND gate selection, programmable. Second degree of freedom for the OR gate selection. But you know, as happens in our country, too much freedom also spoils the whole thing, right? Everybody clamors. So they found it difficult to have people work with this with comfort. They put a restriction now, again back to square one. I will not give you 2 degrees of freedom, I will give you 1 degree of freedom, but the ROM exercise was not good because we had wastage of hardware. This is an inefficiency in hardware. ROM was easy to use. This is efficient in hardware. I will combine these two by taking the 1 degree of freedom from this. So leave the AND array combination to you, and OR array gets fixed. So that is the programmable AND array and fixed OR array. So now in a ROM connection, again I will do the same thing. I will do P0, P1, P2, P3 as functions of f, a, b, c. I will generate the product terms required. But what will happen is they are prefixed. It will say F1 will always be P0, P0, P1. You have no choice on that. So you have to somehow get to a P0, P1, F1 to reduce to P0, P1. If it is not possible, you cannot use this chip. You have to go for a bigger one. And F2 may be P2, P3, or let us leave it 2 now to make it simpler by drawing. Since I want to use the same drawing, I fix which and terms, which product terms go into each of the OR gates. That is fixed. No, it's not negotiable. You cannot negotiate the product terms you can combine in order to make an output. But what you can negotiate is the combination of those product terms itself, the generation of those product terms itself. It is not a min term, it is a product term. You know the difference between product term and a min term. A min term will have all the variables A, B, C, D, E, F along with its complements, whereas the product term will only have those literals which are required for that particular implementation. So now size of the product, size of the ROM would be decided by, now there is no question of common product terms now. That is why I removed this common product term restriction. So I don't have to look for whether something is common between this and this, because even if it is common, I have no way of connecting this and this. Supposing P1 was common to F1 and F2, I cannot combine it because P1 only is fixed to F1, P2 is fixed to F2. I have to make P1 and P2 same. That means I have to regenerate it. I have to generate P1 once for this and once for this. I may call it P2 for convenience. I may call it P2, but I need to if the same AND term, same product term appears in two outputs, I need to generate it for each of those outputs. Is that clear? There is no question of sharing. That takes the burden off. No, when a burden is removed from you, you are happy. At what cost? A little less efficient. That's okay. Hardware is not a big deal, as we said today. So this is what a AND array is fixed. I mean programmable, OR array is fixed. So I will use the same example, except I am going to remove my F4, because F4 I just wanted to show you how to exploit the common terms. There is no question of exploitation here, because if I want to produce no P0, P1, P2, P3, P4, I need to generate 5 product terms called P0 to P4, and I have to combine F1 as P0. This is what it is going to be. Each of these product terms, each of these outputs, let us say, has 2 product terms as inputs. I am going to have an extra product terms called P5. I will redesignate this because F1 can only be P0 or P1. There is only one term required for P0. I will have to not use the other term. Other input will not be used. So P0 will be used. This will have to make 0 because I am not going to combine anything. If I don't combine anything, because the OR is programmable by AND is programmable by us. When I program the AND, I will only program for P0. I will not program for the second term of this. So I am going to redesignate it as P2 and P3 because they belong to for the second output. I am going to redesignate it as P4, P3, P4 and P5. So these two will be F1, F2, F3. So P0 plus 0. Isn't it? So the second term here is not being used. I have only one term requirement, but I have a 2 input gate. I can't do anything about it. I will not use the second input. Here I will use the two inputs. Now if I want F4, which was originally thought as what? What is F4 again? B bar, C bar or BC, is that right? Is that right what we wrote a little earlier? In which case what is B bar, C bar is P2. I cannot use P2 here. I have to redesignate this as P6 and P7 and again generate P6 and P7, even though P5 even though P2 and P5 are available, I cannot use them because I don't have these inputs tied to the next. So if I have a fourth AND gate, OR gate, with 2 inputs, those have to be again programmed for the same variables which are already there. Then it becomes less efficient beyond that. So how will you define the size of this? The size of this should be defined a little more careful. Size should be 3 inputs, four outputs or 3 outputs. There's no contention on these two inputs and outputs. There's no contention. But I need 2 OR gates as inputs to each of these, 2 AND products. So I need to have total of 6 product terms, 2 each for 2 for each output. Of course, there is a standard way of writing it. They will say 2, 2, 2 product terms. When they write 2, 2, 2 product terms, I have 3 outputs. First output will have 2 product terms, second output will have 2 product terms. So I can have 2, 3, 3 or 2, 3, 3, 2. I can have 4 outputs. First can be 2 inputs, second can be 3, third can be 3, fourth can be 2. So again you go through the manual if you want to do it manually or you want to do it in computer. Give the input requirement. Here is even simpler. I don't have to worry about the commonality of these product terms. I am given the function F1, F2, F3, F4. All functions are given. I am told they are 4 variable functions or 3 variable functions or 5 variable functions, whatever it is. I make simplification using corner map and then list them all out, and how to find, supposing I end up saying I need product term for F1 I need 3 product terms, F2 I need 4 product terms, for F3 I need 3, F4 2. Then I say give me an function with 3 inputs or 4 inputs, 4 outputs, 1 2 input, 2 3 inputs, 1 4 inputs. It may not be their exact match. Then you go and get the nearest possible size and do not use, like in this case, I have 2 inputs out of which I am not able to use P1 because my F1 requires only P1, P0. P1 is not used. Like that I may have another product term in which there will be another output OR gate with the 3 product terms. I may have only 2. I may have to put 1 as unused. So the point is the design becomes simpler because there is only one programming step, namely in the OR gate choice. In the AND gate choice, the product term selection, OR gate gets fixed. The second burden of having to identify some common terms becomes less. So this is caught up very well. So programmable array logic is the standard design way of PLD design today. So this is an evolution I talked to you about. PROM design, then PLA design, and then PAL design. Historically it evolved in this way, but what is now popular, if you want to do a combinational design using PAL, programmable logic devices, the most preferred programmable logic device for combinational design today is programmable array logic or PAL. And of course, did I say PAL? That's right, not PLA, because many times I get switch between these two, PAL. So it is programmable array logic. And as I said, there are some problems, but then they say it's simple because of simplicity, and it's also efficient if you know what exactly you want. You can choose the one which is. Earlier we had a variety. Sometimes when you have variety, you have problems. You make an inefficient choice. Here is an efficient choice is possible. So what you have to see is again a little more into this. The most widely used or the most popular programmable logic device, namely PAL, programmable array logic. We look at it a little more closely and see what are the various types of PALs available, and whether we can, how to specify what we need. There are standard procedures for specifying what you need. All that. We need one more lecture on this to complete the programmable logic devices. We will see it in the next lecture.